Hey Royals, in today's lesson, we're going to investigate something known as the conservation of energy. So up to this point, we have two forms of energy that we've discussed. We've discussed the kinetic energy, which we defined as 1/2 the mass of the object multiplied by its speed squared. And we also defined the gravitational potential energy of the object as its mass multiplied by this gravitational field intensity, g, multiplied by its height. Okay, so we're first going to work with these two equations to define how energy is going to change for an object. So we know that if I had an object and I throw it up in the air, it's going to slow down as it rises into the air. So its kinetic energy is going to decrease, but it's gaining height, which means that its gravitational potential energy should increase. Now, same idea if I have an object that's at the very highest point in its motion, it's going to essentially be sitting at a speed of 0. And if I release it, it's going to start to speed up, increasing its kinetic energy as it falls, but decreasing its gravitational potential energy because it's losing height. Right? So what we want to do here is I have a ball. Let's assume that this ball has a mass of 204 grams. So that's 0.204 kilograms. And I'm holding it 3 meters up into the air. And I'll release it. During the time that it's falling, we're going to ignore any air resistance, any energy losses due to sound or friction or anything along those lines. And we want to determine the bulk kinetic energy of the object at each of the positions, so at 3 meters, 2 meters, 1 meter, and once it hits the ground. And I want to find the gravitational potential energy of the object at each of these heights as well. Okay, so first of all, let's think about this. At 3 meters, so I'm going to put h equals to 3 meters. At 3 meters, my height is 3, which means my gravitational potential energy would be equal to the mass multiplied by gravity multiplied by the height. And I put in my number 0.04 kilograms. I multiply that by 9.8 meters a second squared, and I multiply it by 3, and I should get a value of 6.0 joules. So it's telling me that at 3 meters high, the gravitational potential energy of this object is 6.0 joules. And the units is measured right there in the table header, so I don't need to really put it down right now. If the object is stationary at the very beginning, that means that its speed is 0. And we know that if its speed is 0, its kinetic energy must be 0. Right? So if this term is 0, then the whole thing is going to come out to 0. So its bulk kinetic energy is going to be 0 joules. So it's total energy. So if we add this gravitational potential energy and this kinetic energy together, so 6 plus 0, we get a value of 6. Fine. Now let's analyze the situation where the object's fallen 1 meter. So its height, let's draw a line here. Let's say the height is now 2 meters. So the gravitational potential energy that the object has, mgh, is now going to be 0.204 kilograms multiplied by 9.8 meters per second squared, multiplied by a height of, it's only at 2 meters above the ground now, so 2 meters. And I work that through and I get 4.0 joules. So that means its gravitational potential energy is now 4 joules. Let's determine what its bulk kinetic energy is at that position. So to do that, I need to determine how far has the ball moved. So under the influence of the force of gravity, this ball is going to accelerate as it falls downwards. So I need to say that its final velocity, v2 squared, is equal to its initial velocity, v1 squared, plus 2a delta d. Now v2 squared is equal to 0 meters a second, because initially it's stationary, plus 2 multiplied by 9.8 meters per second squared, and the distance that it's traveled. It started at 3, and now it's at 2, so its change in height or change in position right now is 1 meter. So V2 squared is actually going to come out to 19.6 meters per second squared. Or sorry, meters squared second squared. And I'm going to keep it as V2 squared. And the reason for that is that when I substitute it into my kinetic energy, I have 1/2 mass multiplied by V squared. I'm going to keep that squared. So when I substitute it into my kinetic energy, I don't have to find the square root and then square it again. So I get 1/2 0.204 kilograms, because my object's mass doesn't change, multiplied by 19.6 meters squared times second squared, or divided by second squared. And when I multiply that through, I get 2.0 joules, which means that my kinetic energy at this point is 2.0 joules. And if I look at its total energy, it started with, at this position, it has 4 joules of gravitational potential energy. It has 2 joules of kinetic energy, which means that its total energy here is 6.0 joules. And I'm going to ask you to pause the video. Try to find out the gravitational potential energy at 1 meter above the ground and at 0 meters above the ground, so on the ground. And I want to find the bulk kinetic energy at those same positions, at 1 meter above the ground and as the ball is hitting the ground. And then calculate the total energy of the object, similar to how we did it for at 2 meters. So again, pause the video, try to fill in the rest of the table, and then come on back. So welcome back. So you may have noticed something. The total energy of my system always was 6 joules. And the amount of energy that my gravitational potential energy lost, the kinetic energy picked up. And so that makes sense. As the object is falling, it's losing gravitational potential energy, and the amount that it loses gets transferred into kinetic energy related to how fast it's moving, right? So this can actually be written as an expression. And we say that the addition of the kinetic energy and the gravitational potential energy is the system's mechanical energy. So we say mechanical energy, or the total energy that the object has, is equal to its gravitational potential energy plus its kinetic energy. And that's what we mean by its mechanical energy, right? So the energy that an object has at the very beginning. So if we look at the system here, it had 6 joules of gravitational potential energy at the very beginning. No energy in motion because I'm holding it still, but as it drops, this energy changes and they keep the balance between the two of them so that my total energy always added up to 6 joules. So as an expression, I can say that the total energy at one position, so the total energy at the very beginning, is equal to the total energy at the very end. So ET total at the end. Written as an expression, full out, I can say that the kinetic energy that the object might have at the very beginning, so EK1, plus the gravitational potential energy that the object might have at the very beginning, EG1, is equal to the kinetic energy that the object has at the end, EK2, plus the gravitational potential energy that the object has at the end, EG2. So this is what we mean by the law of conservation of energy. It says that energy cannot be created nor destroyed. It just transfers from one form to another. Okay, so in some expressions, we might have the case where we're losing energy due to friction or sound or light or some other source, and we write that as plus work. So work means that there is energy leaving my system or added to my system. Maybe I'm pushing the object, speeding it up, and I'm applying a force on the object. Maybe there's friction, which is removing energy from the system, which means that work is being done on the system, or work energy is being removed from the system. Okay, so let's put this into an example of a roller coaster. So in Sandusky, Ohio, there is a roller coaster. It's called Top Thrill Dragster. And for a period of time, it was the world's fastest and tallest roller coaster. And what it does is it has hydraulic motors that launch a cart full of people forward, and then the car will just go straight, almost straight upwards, do one barrel roll, and then come straight back down. And as it does this, the energy is being transferred from kinetic energy into gravitational potential energy. And we want to find in the first part of this question, how high would the roller coaster go? Or like, how high can I build that first hill? So if I'm launching the roller coaster forward, it gets just to the very top and then goes over. So essentially the velocity at the very top, or the speed at the very top, is 0 meters a second. Okay, so let's figure this out. At the very beginning of this situation, if I have this as my first bump in my ride, at the very first location, I have a speed that is 57.2 meters a second. I know that my roller coaster has a mass of 6,300 kilograms, and it has a height of, let's call it 0. Let's define the initial height as 0. So any height that I calculate, i.e. the top of the first hill, will be what we'll call h2. It will be the height of that hill. And we're going to say at that location, the speed will be 0 meters a second. Is this going to get to the top, just become 0, and then fall over the other side? So we're going to use conservation of energy to determine the maximum height. So using conservation of energy, I'm going to say the energy at the very beginning, at the bottom of the hill, ET1, is equal to ET2, the total energy at the top of the hill. So that tells me that I could potentially have gravitational potential energy at the bottom, plus the kinetic energy at the bottom. And that's going to be equal to the gravitational potential energy at the top, EG2, plus the kinetic energy at the very top of our hill. So energy must be transferred from motion into our height. So at the very bottom, mgh1 plus 1/2 mv1 squared. That's all the energy the object or the roller coaster had at the very beginning, is equal to mgh2 plus 1/2 mv2 squared. That's the energy that the object would possibly have at the top of our hill here. So if I substitute in the fact that h1 is 0, this term goes to 0. And we're also using the premise that the very top, the speed of our roller coaster essentially goes to 0, which means that this term is a 0. So realistically, we have this kinetic energy, mv1 squared, is going to be equal to mgh2. So let's substitute in our values. So we have 1/2 of 63,000 kilograms multiplied by 57.2 meters a second, and I square that, is equal to the mass 63,000 kilograms multiplied by 9.8 meters per second squared and multiplied by h2. So the left hand side here comes out to 10,306,296 joules. And the right hand side becomes 61,740 newtons multiplied by h2. Dividing this through, we get a height of 166.93 meters. So that's telling me that about 167 meters would be the height that the roller coaster can actually get to. Okay, so the second problem says, what if there was a second bump? And that second hill was a height of 45 meters. So we're assuming that we went over that first hill, and then the second hill has a height, let's draw it a little bit bigger. First hill, and then the second one is a height, we'll call it H2, because it's a new problem, we'll call it the final height is 45 meters. The initial conditions of this situation, the cart still leaves the station at 57.2 meters a second, and it leaves with a height that we'll call H1 of 0 meters. We want to know how fast is the roller coaster going over that 45 meter tall bump. I can ignore this first hill because I'm saying that the energy that is here at location 1 has to be equal to the energy at location 2. Okay, so I'm going to work through this problem the same way we did the first problem. So I'm going to say the energy total at location 1, that's just leaving the station, has to be equal to the energy at the top of that 45 meter tall second hill. So the first situation, I have the gravitational potential energy plus the kinetic energy as the object leaves my station, all position 1. And that's going to be equal to the kinetic energy plus the gravitational potential energy at location 2. That's the top of that hill, that 45 meter tall hill. So let's write our things out. mgh1 plus 1/2 mv1 squared is equal to 1/2 mv2 squared plus mgh2. Now let's think about the situation here. The initial height of my object is 0, which means that the initial gravitational potential energy is 0. I can't really get rid of any other terms because nothing else is 0. So in this situation, I have 1/2 the mass multiplied by v1 squared is equal to 1/2 the mass times v2 squared plus mgh2. Let's multiply every term by 2, which means I get mv1 squared is equal to mv2 squared plus 2 mgh2. And I notice that every term has an m, so let's divide everything by m, which tells me I get v1 squared is equal to v2 squared plus 2gh2. And I want to find v2 squared. So that tells me I can go v1 squared minus 2mg, sorry, not mg, I have 2gh2 is equal to v2 squared. So let's substitute in our values. I'm going to run out of space, so I'm going to come over here. I'm going to say that I'm substituting my values. V1 was 57.2 meters a second squared minus 2 multiplied by 9.8 meters per second squared multiplied by the height of that hill, 45 meters, will be equal to v2 squared. Working that through, if I were to do that, I get the left-hand side coming out to 2,830.84 meters squared divided by second squared, and that's equal to v2 squared. Square root of that tells me that I have a speed of 53.2 meters per second as the speed of my roller coaster as I go over that second bump. Okay, so big picture here, I'm saying that the energy in our system cannot be created nor destroyed, which means that the energy at the very beginning of our problems has to be equal to the energy at the end of our problems. The energy only transfers from one form to another, and we could possibly run into situations that has friction pulling energy away from our system, or there could be an external force causing the object to increase the amount of energy that it has. So you're doing work on the system. So as always, if you have any questions, please don't hesitate to reach out to me.